together. But y'all, that's not the way that this district does it. They do partial pressure first. So you literally are adding and subtracting today. That's it. Like it's really that simple. You just have to figure out what are the things that you need to be adding, and then what should they total up to, or if you have a total and you know some of the things that you're starting out with, like what's the missing value, like that's really all we're doing today. However, if we know all of the gas laws, then you have to be able to use the balanced equation. You have to be able to use all the other different formulas. So it's just a different order, but that does make today extremely simple for you guys. I don't think I made a mistake with the opener. Oh, there's somebody else that wants in. Like I did with Earthspace, my text box thing was not done right. And I think I put all this stuff in blue. I just caught a couple things that I didn't. But we are doing something called Dalton's Law of Partial Pressures today. And because you don't know any of the mini gas laws, I can't do any of the hard math. Like I said before, when we started up the second semester, almost this entire semester is math. Now, I like the gas laws because most of them are set up like a proportion where you cross multiply and divide by the odd man out. If you've never been shown how to do that, I'll show you how to do that. But this one doesn't do that. So for the opener, let's see, what does increasing the temperature of a gas inside a container eventually make the container, let's just say why does increasing the temperature of a gas inside a container eventually make the container burst? So why don't you, if you have a hairspray, like an aerosol hairspray thing, and it's empty, why don't you throw it in the fire? Why does it explode? It builds up the pressure of what is left inside the can. Even if you're pushing the nozzle and nothing's coming out, there's still gas inside the can. It's just the same pressure as the air outside the can, so nothing's coming out. But if you throw that in a fire, please don't go test this at home. If you throw an empty aerosol can in the fire, it will eventually explode. Because when you heat up the gas, it increases the pressure, it pushes against the inside of the container, and eventually it can't hold it back anymore and it'll explode. Don't try that at home. Please.
Too late.
So what is, and this should say why, not what. So I've already found a typo. So what is actually happening inside the container is the pressure, the temperature increases the energy of the particles. They move faster inside the container, which means that there's more pushing on the inside of the container, which increases the pressure. That's what's happening. You just can't see the little particles moving around inside. And this really should not take us very long to go through. I don't even know why I put gas pressure on here twice. I need to take that off. What gas pressure is, okay, is the pressure of the particles, okay? Like it could be, They're both up here if you need the paper ones. But you can't normally see a gas particle. Like there's all different kinds of gases that we're breathing right now. It's not pure oxygen or we would die. Okay, pure oxygen will kill you. So we've got oxygen gas in the air. We've got mostly nitrogen gas. 80% of what you breathe is actually nitrogen gas. We've got carbon dioxide gas in here, maybe a little bit of helium gas. Normally helium and hydrogen escape the atmosphere. But there's other gases that we're breathing. And the faster they're moving, the more energy they have, and that's going to increase your pressure. Now, there's different ways to change their speed. Now, we normally talk about a rigid container, okay, so not like a balloon, okay, not something that you can squeeze and that can expand, like a can, you know, or a vault, or like if you've ever been scuba diving, the tanks that you put on that let you breathe underwater, those things don't expand and contract. So this picture, which I think you have on your notes, is supposed to represent the different gas particles and how they're all moving in different directions independently of each other. I don't know what kind of gas that is, and purple balls with arrows pointing their vector at which they're traveling. But I can do things to that gas to change their speed, and changing their speed is either going to increase or decrease the pressure of the gas inside the container. This is how hot air balloons work. Have you ever been in a hot air balloon? No. Really? They're very peaceful until they pull the thing. It's a right in your ear. We had friends of the family that used to repair hot air balloons. And they used to bring us home via hot air balloon if the wind was right. And they could land in the field behind where row houses were. It was awesome. And then their barn burned down. So then they lost their business, which is sad. They're lucky they didn't lose any of their animals. All right, so what would be the effect of adding more gas to the container? Okay, so rigid container, and somehow now you put more gas inside it. What would happen to the pressure? It would go up because you have more stuff. You have more stuff, they're still going to be moving at whatever speed they're doing. We're not going to calculate it. Is that a Google Meet doorbell? Hold on. That's what it sounded like. Yes, it was a Google Meet doorbell. I'm trying to off for a week, and I'm not used to all the different bells and dings and all that good stuff. Okay, so yes, if you increase the sheer volume of gas, you're going to increase the pressure inside the container. Yes?
No, never mind.
I should go in the right order. Okay, and so if you don't change the amount of gas, okay, so that now it's constant, but now you make the container bigger, what would happen to the pressure of the gas? It'll go down because now there's more room for those same particles to bounce around inside the container. I may have to come back and do the kinetic theory of gases when we do the combined gas law. Like I said, I like gas laws. Easy now. So now, same container. Okay, I'm not changing the size now. And this was the opener. But now I start to heat it up. What would happen to the pressure? It'll go up. Now, what causes heat is motion. It's like when it's cold and you do this, and your hands heat up, it's because of the friction. It's because there's more kinetic energy. Warmer air moves faster than colder air. Warm air rises and cold air sinks. They're all things that you should have heard at some point in time by now. You do not know that, okay. Hope you don't have a house fire then. Oh, that's why you crawl, because the smoke and the heat's supposed to go up. Okay, so once again, if you have an increase of the gas, pressure goes up. You have an increase of the temperature, the pressure goes up. If you would decrease the size of the container, the pressure go up. But this question says what would happen if you increase the size of the container? And that means that the pressure would go down. So that means if you reduce the temperature, the pressure goes down. And if you reduce the amount of gas present in the container, the pressure is going to go down. It's just how often are these gas particles hitting the sides of the container, which is what causes the pressure in the first place. This is probably the most you're going to write. Most of the other stuff is short. A couple sample problems. I'll show you how to convert between the pressure units, because there's 4. I'm only used to teaching 3, but for some reason this district likes to bring in the torr, which I think is stupid because it's the same thing as a millimeter of mercury, but they talk about it. And we do not do pounds per square inch because that is standard and science is metric. So we don't do pounds per square inch. Yeah, was there? No, there was a question. And I don't know if any of you have seen a barometer. I have a barometer actually.
Oh.
Barometer. Measures air pressure. Air pressure. It's not one like my parents had. This is just an old school. So what's we are at 995 millimeters of mercury right now, which makes sense. That's lower, but we're having a cold front. We're not gonna. There's not gonna be like all the ice and stuff. But when the cold fronts are lower pressure and warm fronts are higher pressure. I know all about that crap because I had to deal with hurricanes. There's a hurricane out there and you got a low pressure over top of your head. You need to leave because that sucks them right in. Things always go from high concentration to low concentration. They go from high pressure to low pressure, from warmer to colder.
I'm 57 degrees outside. I'm wearing shorts and a t-shirt with no jacket. It'll be a fun walk home, guys.
Sorry. It's supposed to rain like all day too, just so you know. Like not like, well, it's supposed to be thunderstorms later too. Right now, it's just like an annoying, misty, light rain drizzle. All right, so y'all, we have 4 major units for pressure, okay? And the one that the barometer, the one that little dial was that I just read is measured in something called a millimeter of mercury. MM for millimeter. Mercury's symbol is Hg. It's short for hydrogyrum, which is Latin or Greek, one or the other, for liquid silver, which is what mercury looks like. And the one that I like to use the most is the atmosphere, or ATM for short. Not like the thing that gives you money. It's an automatic teller machine. But I prefer to use atmospheres. If I have a choice of using any of them, that's the one that I will pick. Because at standard temperature and pressure, that thing's value is a 1. And it makes it a lot easier to do your math if you multiply or dividing by 1. The torr is one that I don't normally use, but it is a unit of pressure. And then there's also kilopascals. Now, when we do gas laws, depending on which pressure you're in is going to determine which rate constant you have to use. But we're not going to do the ideal gas law until next week. We are doing the 3 baby laws this week. And like I said, I'm not used to doing partial pressure first. I'm used to doing it last, but that's okay. Just makes the math easy for you guys. But these are the 4 different units. Oh, I'm sorry. I do have them all. When we are doing measurements, normally it's going to mention things being at STP. It was just a band from the 90s, but that's not what it means in chemistry. It's short for standard temperature and pressure, where we're at a specific temperature and we're at a specific pressure. Now, there's 4 different types of pressure, so there's 4 different numbers. You mean to go back one?
No, you can go back.
Go forward. All right. So at sea level, which we're about 721 feet above sea level. I had to look that up today for my Earth space class because I didn't know what the elevation was here. But that's where we are. We're above sea level. But if you're at the beach and you are at sea level, you're going to be at what's called standard pressure. Standard temperature is a very specific temperature. It's about room temperature for us, 20 degrees Celsius. You don't need to know that part quite yet. But what you do need to know is that these are all equal to each other. Oh, please don't kick me out of my room.
Please tell me I'm not going home.
No, it looks like
Please come and go home.
That's me.
This will be the 4th time.
it's you.
Yeah.
Bro, why are you leaving? Sure thing. Jimmy, you're being signed out.
See? No.
No. They wouldn't do that. That would be a pass if it was COVID. Okay, so you need to know that these are all equal to each other. And they take it out of chemistry and out of pressure. That's like saying 1 foot is 12 inches. Okay, different unit, different number. So 1 atmosphere, that's the one I like to use if I can choose. 1 atmosphere is the same thing as 760 millimeters of mercury, is the same thing as 760 torr, is the same thing as 101.3 kilopascals. They all mean the same thing. They're all standard pressure. The hardest part about the gas laws is, first of all, making sure you're in Kelvin for temperature. I will show you how to do that later. It's not hard. Kelvin is the temperature scale that we use in gas laws because it doesn't go below 0. There's no negatives in the Kelvin scale. It's not hard. Trust me, it's not hard. But you have to make sure that your pressure units match. If they don't, you have to convert them so that they do match. And I'm going to show you how to do that in just a second. This is an old school barometer. The one that I showed you that I picked up over there is a dial, but it basically works the same way inside, where the air is pushing down on the mercury, which is inside the barometer, which then forces it to rise in a column that we can measure, sort of like taking temperature, but it's not temperature, it's pressure. That's how the old school ones work. My parents have got one on their wall, and I'm sure it's got mercury inside it, but you can't get your hands on mercury anymore because it's toxic and it will first make you go completely and totally insane, and then it will kill you.
At least I have fun before I die.
No, not like a fun crazy, like an insane crazy. That's why the Mad Hatter was called a Mad Hatter, because they used mercury to process animal fur to turn it into felt, and they all went cuckoo for Cocoa Puffs, and then they died.
You had fun though.
All right, so I'm gonna show you how to convert real quick. We're gonna convert 895 millimeters of mercury to torr, which is easy. And we're also gonna convert 895 millimeters of mercury to atmospheres. So-
This walk kind of cold.
Right. So that means we would drop the 895. I'm going to do the top one first, but we would drop the 895 in the starting block. These conversion crosses, we use them all the time. We don't want to be in millimeters of mercury, okay? And I want to be the top one. I want to be in torr. Well, if you just wrote down how they were all equal to each other, what was the number in front of the millimeter of mercury from the 4 conversions that were in a row that was on the previous slide? What was the number in front of mmHg? You just wrote this down. 1 atmosphere was equal to something was equal to something. What?
Oh,
760. What number was in front of the torr? Also 760. That's probably why I don't ever remember teaching torr, because like it's the same dang number. So 760. Both millimeters of mercury and torr, its numerical value is 760 at STP. These divide out. Or you really could do 895 times 760 divided by 760, but they cancel out. So it's 895 torr. That's not going to be quite as simple for changing it to atmospheres. You're still going to drop millimeters of mercury. I'm going to bring it to atmospheres. Millimeters of mercury still gets 760, but the atmosphere gets a 1. So you would do, you don't have to do times 1, but 895 divided by 760 is going to be 1.18 atmospheres. You have to be able to switch between them. And you get the numbers that belong here from right here. They're all equal to each other. From above the picture of the barometer. Okay, now, being able to use these for partial pressures. John Dalton, not John Dalton, different Dalton. John Dalton was way older. You're going to see that certain things are constant when we do the gas laws, like the ones that actually have a formula. You're going to see only certain variables are mentioned. If it's not mentioned or if it's constant, it's not going to affect your math. With the partial pressures, we're going to assume that the volume is not changing. Okay, we're not making the container bigger or smaller. It can't expand or shrink. We're not going to change the temperature. And the pressure is just going to be, you're going to add up each individual partial pressure. Like you're literally adding and subtracting. Sum, you add. If you know the total pressure, and you know all but one of the individual pressures, then you're going to subtract those from the total. It's literally all you are doing today. Let me double check my attendance online here real fast. Okay, because I only saw Declan online, and I know other people came on. You got Alexis and Veronica. Alexis. And then in here, George, don't see this one. Bailey. I thought I saw Bailey online. Okay, I'll have to check her real quick. Tiffany, Luke, I think got in trouble. I don't know. They don't tell me. I just see if somebody's here. Some Sebastian's here. Matthew, no. Caitlin, yes. Logan, yes. Jared, yes. Mia, yes. Tatiana, no. Aiden is back. Valerie, Robert, no. Reagan is here. Slate is here. Jimmy just left. Kyle, Jeremiah. Okay, I got everybody now. All right, so let me show you how to work this thing. I mean, there's no formula. All of the other gas laws have an equation. Don't let it scare you. They're like very easy to manipulate formulas. So we're going to determine the total pressure in millimeters of mercury, torr, and kilopascals of a mixture that contains oxygen, nitrogen, and helium if the partial pressures of the gas are as follows. So I know my partial pressure, which is what the P is, of oxygen gas. You could do like O2 instead of writing out oxygen. That's fine. Its part is 150 millimeters of mercury. I've got nitrogen. Its portion of the total is 350 millimeters of mercury. And I've got helium. Its portion is 200 millimeters of mercury. Well, I guess I only calculated it for millimeters of mercury. I'll convert them on the board. I didn't put them on the thing, so I'll have to talk through it. So to get your total pressure, it's going to equal to the partial pressure of oxygen plus the partial pressure of nitrogen plus the partial pressure of helium. And all I did was changed it from the word to the symbol. And we know that oxygen gas and nitrogen gas, there's always two of them. Helium is not one of those 7 special elements. No, you're just going to add. Literally, you're going to add 150 plus 350, which is 500 plus 200 more is 700 millimeters of mercury total. Well, it's just the pressure. Now, to change it to the other ones, now I don't need to do anything for torr because the 760 and 760 cancels out. So this is equal to 700 torr because they cancel out. To change it to atmospheres, it would be 700 millimeters of mercury. It's got a coefficient, or it's not a coefficient, but it's 760. Hg, 1 atmosphere. And then to change it to kilopascals, I'll have to grab my calculator in a second. I still know this is, I'm running out of blanking on this. And it was 101.3 kilopascals. Let me throw this one away. It's dying. Okay, so on the board, for those of you that are remote, because I didn't put this on here, I'm converting out to the other, let's see, 700 divided by 760 is going to be I'm going to go ahead and do 2 sig figs. 0.92 atmospheres. And then 700 times 101.3 divided by 760 is, I'm going to put one number after the decimal, 93.3 kilopascals. So that would actually change it into the other two because I just now noticed that it says it up there and I didn't do it on the screen. But you do have some questions at the bottom that are just convert this, like whatever the starting pressure is, into the other ones. And like I said, you're getting these conversion factors from right above the picture of the barometer on the other side. Now, there will be a time when it's not a standard temperature and pressure. Later on, I will teach you how to do that. At least I think this district does. We haven't gotten that far into our planning. The next problem, I have a container that contains a mixture of gas. I know the total pressure is 302.5 kilopascals. I know a known gas pressure for oxygen. Its partial is 107.8 kilopascals. My nitrogen gas is 102.6 kilopascals. And I want to know the pressure, which is going to be in kilopascals, because all of the other pressures are for whatever the mystery gas remainder is inside this container. Okay, so I know X is the mystery gas. Oh, that should have been a subscript. There's another typo. I'll fix it. So I know my total was 302.5. I know the part that's oxygen, 107.8. I know the part that was nitrogen, but I don't know mystery gas X. So you can either go ahead and add these and then subtract it from both sides, or just do 302.5 minus 107.8 minus 102.6. But when you subtract them, my mystery gas, whatever it is going to have a pressure of 92.1 kilopascals. Sometimes I see the K is capitalized. Really, kilo should be capitalized, but normally with this, it's lowercase. If you capitalize it, I am not going to count it wrong. It is literally what you are doing today. You are either just adding them up to get the total. Just make sure that your pressures are the same. Let me make sure I wasn't that mean, because I bet you I was. Atmospheres, that's okay. Atmospheres is okay. Okay, so number 3, it even says, make sure you convert to atmospheres first. So you've got one gas that has a pressure of 401 millimeters of mercury. You need to change it to atmospheres first and then use that to get your answer. This is not the right answer for it, but this is how you would convert, where the 760 would be on the bottom and then the 1 would be on the top. Number 4, atmospheres. atmospheres. That's it. And then number 6, you're converting the 1189 millimeters of mercury to atmospheres per and to kilopascals. Make sure you are showing your work. I did not give you answers on this one because you're just adding and subtracting. Now with the, let me stop the recording. With the other gas laws,